Today we're going to be talking about related rates. This is how the rate of a reaction or the rate of formation of one reaction component relates to the rate of formation of a different reaction component, and how each of those might relate to the reaction rate or rate of reaction. So we can monitor this reaction as a function of any of these reaction component concentrations, but we have to relate them back to each other. We have to keep in mind that they have different rates, right? So the rate of disappearance of N2O5 will be twice the rate of appearance of oxygen, because when two molecules of N2O5 are lost, only one molecule of oxygen is formed. So oxygen should form at only half the rate that N2O5 is lost. Also, NO2 will form at 4 times the rate that oxygen forms because of the stoichiometry. I have a little cartoon. I've simplified the molecules a little bit to make them easier to see. If we could keep these in separate flasks, which of course we can't, but let's pretend we can, we'll start with just our reactant. And as the reaction proceeds, what you should notice is that NO2, the blue spheres, are at a much faster rate than the green spheres. And of course, the disappearance of spheres is than the rate of the other two. So depending on the one monitoring, we have to be able to relate that back so that if we all came in the room together to talk about the rate of this reaction, we would be comparing apples to apples. I can't talk about the rate of formation of NO2 and somebody else be talking about the rate of formation of oxygen when we have to make sure we understand that they're not the same. We have to relate them back to each other, and we have to what's called normalize our discussion. So we're going to talk about related rates and a related rates expression. The first thing we're going to start with is our generic reaction. We're going to be using this reaction a lot in the future. Lowercase letters are stoichiometric coefficients, so those are going to be numbers. And the uppercase letters are going to be reaction components, so those are going to be molecules, compounds, elements, whatever is in the reaction. A and B are reactants, C and D are products. Our related rates expression, we're going to write next based on this syntax, with lowercase letters being stoichiometric coefficients and uppercase letters being reaction components. Rate of reaction is whenever you see that term in a table or someone asks you about the rate of reaction, that's what that means. The stoichiometric coefficients are the lowercase letters, and so you can see the -1 over lowercase a. Those lowercase letters are all the stoichiometric coefficients as they appear in the reaction, in the balanced reaction. And remember that the brackets mean molarity, and so those are change in molarity of A over change in time, change in molarity of B over change in time. These negative signs for the reactants are negative because the rate of reaction is always positive. But the change in reactant concentration over change in time is a negative number because reactants decrease over time. So to make them positive, we put a negative sign in front of that. Okay, so let's practice one with a real reaction, like our favorite reaction here. We're going to write the related rates expression for this reaction. So here we are. The rate of reaction on the left. Don't forget to write rate of reaction, because I might ask you a question. I might say, calculate the rate of reaction, and you're going to say, I don't know what you're talking about, and you'll forget that left side of the equation. Rate of reaction equals. So now our expression with actual numbers in it is -1 over 3. That's because the stoichiometric coefficient in front of hydrogen was a 3. And then delta H2 over delta T, that's the change in hydrogen concentration over time. Or you would also call it the rate of change of hydrogen concentration. And then negative delta N2 over delta T, there's no fraction there because there's no stoichiometric coefficient, it's a 1. And then positive 1/2 change in concentration of ammonia over change in time. So those 3's go together, right? There's a 1 in front of the N2, which is why there's not a fraction there. And then the 2 in front of ammonia becomes a 1/2. And that last one is positive because it's a product. And the first two are negative because they are reactants.